Hello. Thank you for staying late for the session. I know the traffic here is beautiful. I hope this is worth it. I had to drive from Fremont here in the morning, and I got here right on time. I was planning to be 1 hour early, so it's always amazing. So thank you for staying late and watching this. I hope this is entertaining and interesting. This is a presentation I'm going to split with the Couchbase. My name is Ivan. I work at Google. I'm going to talk a little bit about the cloud platform that we offer. A lot of people don't know we have it. I happen to have a very good friend that works on Couchbase, and the reason I'm here is I lost a bet. I will explain the bet halfway through the slides, but I want to talk a little bit about the product I sell, so you guys know it's a good option for you. I think we all kind of saw what you see on the slides right now. We want capacity, we want machines, we want the resources we need to do prototype right now. No one has the patience to go through a procurement process to get machines or to talk to the IT department to get a database. Right? You can very quickly go out and get your resources and do the prototyping. And almost none of us want to actually pay the depreciation of equipment. You buy the equipment, you do the capacity planning, you might buy by peak, and then you have to pay the depreciation and the cost of all that. And if you're a startup, for instance, and you're building your product, it's very weird for you to look into the balance sheet of your startup and see CapEx, right? Because it's very hard to get rid of this stuff, right? So one of the things that cloud products offer is they offer this cost structure that is essentially different and more flexible. So this is something to take into account when you go and invest and you decide how you're going to build your startup. And prices continue to drop. So Google had a fairly significant price drop a couple weeks back. And then if you go back 3 months back, we did another price drop. So this is getting cheaper and cheaper and cheaper. And at some point, you're going to see that it's actually cheaper to rent a VM than to actually buy the machine and have it. One of the other things I want to talk about is like this optimism message that is change is accelerating. And change is accelerating is a good thing for people that try to create new things, right? So there's this famous phrase, or at least for me, that we kind of like tend to underestimate the amount of change that happens in medium term, right? We overestimate what we're going to do tomorrow, and we always miss. Developers are the most optimistic people on earth. I don't know anyone that would be so wrong about deadlines like developers. And next time you're optimistic again, because it's part of us. We want to build stuff. But then we tend to underestimate how much change happens everywhere over like 10 years. And this is my favorite slide of all my slides, right? What this thing is in 1957, you look at the SP 500, and the average age of the company on that was 75 years. In 2003, the companies were 25 years old. And then in 2013, the companies were 10 years old. Right? So this means that in 10 years, we're going to have a huge shuffle of what are the companies that are the biggest, more important companies, at least for the American company, right? So this is an indicator of a lot of churn, a lot of opportunity. And I don't think I have to say that I think technology will play a big role in this. Google has been working steadily for the last 15 years. A lot of this was quietly. We didn't have a public cloud for most of this time, but we've been building this internet to make people watch cat videos very quickly. They get really mad when the cats buffer, so we've been investing a lot of networking, and we have agreements everywhere. We have very efficient data centers. Google, the founders and all of Google really care about being green and efficient, so we really care about our cost structure as well. Google is very famous for like lavish treatment of employees, so we kind of like our margins. So we like to have very efficient data centers, very cheap machines, very cheap infrastructure that's too efficient for us. We've been building this for our own use, and a few years back, we decided to go out and share this with the community. There's a tradition of Google of sharing what we find out. So a lot of the NoSQL databases that you see today, they start to be developed when we publish the big table papers. Right, so this is a traditional Google, and you can see that over the years we've been very busy doing new things. And I wanna show a slide deck. The next slide deck. The next slide is kind of an interesting one. So I want to make this interactive. Right? Who here heard of Google Cloud? All right, that's true. 70%. Does Google have more or less than 5 products on Google Cloud? Who thinks is more? Less or fewer? I speak English. Fewer, all right. So is it more or less in the ballpark, 5? All right, so 5 is what we shipped in the last 12 months. So at this point, Google Cloud has a very rich portfolio of applications. And the reason we're able to do this is we're taking the 15 years of investment that we have on the company, and we're making sure the products are polished enough. We're adding the proper load isolation, the proper security, the proper auditing, the proper things to enable us to go and sell this as a product. And this is what we're doing. And where we have gaps, we either build them or acquire them. One example would be the little thing that looks like a honeycomb over there. It's Firebase, which is a fantastic thing for notifications on Android and mobile. And this slide tells what my day job is. And this is where I'm going to tell the bet I lost. So I'm the technical lead for the, cloud performance. So basically what I do day in and day out is I profile our products, and we find a way to make them faster or cheaper to operate or something like that, right? And we translate that into price cuts for you guys or gains for us. And one of the things that we do is we do benchmarking. And we do benchmark all the cloud providers, and then we set the prices, and we make sure that we offer more value than our competition. And as part of this, I end up writing a benchmark for a competing product that was not Couchbase. And I publish a blog post. And my good friend at Couchbase says, we can do better than this. Your results are ridiculous. And I said, no way. You might beat me by a little margin. And he said, no, I'm going to beat you, and you're going to be ashamed of what you did. And I said, no way. So, you know, harsher words were used. But I'm on video. And end of story, he said, you know, if I win this, you're going to go be shamed in public in one of our events. So I'm here to be shamed in public. I lost a bet. Congratulations, you guys did a great job. And this particular benchmark that we did exercises a part of the Google platform, specifically compute engine, which is like you can go and rent a VM from us. We have a very rich portfolio of products. We support you all the way from App Engine, if you ever heard of it, which basically write the code, we manage everything from capacity to utilization to failures to restarts to all the stuff, but you kind of don't have the same level of application compatibility with traditional development. All the way down to we have load balancers that will increase the number of instances you have, all the way down to, okay, you rent a VM from me, right? Even when you go to this lowest level of service, which is like I rent a VM, I get a VM, I'm going to use this thing like I was going to use a server, we try to do things to add value to this. Right? So this is what the value proposition is. I think if you ask anyone that rent VMs, they will have a similar set of bullets. But we have little things that make things easier. Right? So we have actually billing in few minutes increments. So if you turn things up on and off, we stop charging as soon as you turn them off. We have this magic hard drive that goes all the way to 10 terabytes. I'm going to talk about this a little bit. A very rich set of VMs. We try to be very transparent about what you get when you get the VMs. Load balancing. We have everything is encrypted at rest. We have quite a lot of stuff that is encrypted in trances as well. So if you use Google Cloud and Couchbase and you add encryption, you're going to encrypt the encrypted stuff. So it's double gibberish when you get back. By the way, for last time I heard someone say, "Oh, if they go in the data center and steal a hard drive, if someone gets into the Google data center and steals the hard drive, I'll give them $100. I am not very good at bets, but this one, I am not losing this money. Go online and look at the pictures; they're really well guarded. All right, so here's my magic hard drive. You go out and you get one of our VMs and you buy a hard drive and you say, wow, I have a hard drive. Fantastic. I'm going to put a file system in it and I'm going to use it. Even on the lowest form of service that we offer, which is the VM, this is what my mental model of a hard drive is. The mental model is I have a set of platters. They have concentric cylinders. The cylinders are divided in logical blocks. They are monotonically slower as you get closer to the center of this. So I'm going to make sure I have a smart scheduler that are going to reorder my IOs to put them in order. I'm going to separate sequential from random. I'm going to do all the stuff. Unfortunately, or fortunately, because you don't have to think about this stuff anymore, when you buy a hard drive on Google, what you get is all those magical blocks spread over a few thousand servers. So actually, the throughput of this thing is really limited by a piece of software that limits it. So this is the real interesting thing about what we're doing with the cloud. None of our devices are actually the devices you used to. I have a much longer presentation where I go in detail what the differences are, but this is a very cool thing. If you guys want to try the Google Cloud Platform, I might have lost the bet, but I'm not done. But I have 2 guys that are Google sales engineers on the back. They have fantastic free credits that if you want to try it, you can try it. You can make fun of me, but I'm doing my business. Yes. All right, so this is what those disks kind of look like. We have both the standard, what we call standard persistent disk. This is spinning media. It's backed by thousands of servers on a farm. Your logical blocks are spread all over there. So if you steal any one disk, there's nothing useful there. You're going to be sharing that with other people that have fractions and fragments of encrypted stuff there. No hotspots, very nice thing about this. If you, like the LinkedIn guys, hammer the SSD version of this that's in yellow, it's not going to burn out because it balances out across different workloads. And then we have actual local SSDs that can go all the way to 800,000 IOPS, which is more than most applications will generate. It's very difficult to actually consume that amount of I/O. At some point, we look at each other and say it's kind of ridiculous to improve this. Right? So we work on latency instead. And now I'm going to pass to so David can talk about what they did that was so amazing that made me come here.
Thank you, Ivan. Okay, so I work for the Couchbase team based in the UK, and many of our customers are deployed on cloud-like infrastructure. And so we became aware of the Google Compute platform. We wanted to see how well Couchbase performed on it. Furthermore, our interest was piqued by Ivan's blog post where he claimed that he could, and this was the challenge that was laid down, perform 1 million writes per second with a mere 300 nodes. This is what gave his friend at Couchbase the confidence to go, you know what? I'm pretty sure that's a bet we can win. And so we're very appreciative. You've been such a good sport and taking this on the chin. But so there were a couple of our competitors also joined in the fight, and so we were interested. We pride ourselves on our leading performance and scalability, so we wanted to see how well we would measure up. So a first few words on benchmarks in general. It's really nice to see that the benchmarks in the NoSQL industry in general are really hotting up at the moment, with many people regularly publishing the latest and greatest figures. But let's be honest, there's a game that we all like to play at times, which is we ran a workload that suited us, We ran our competitors, and guess what? They sucked, and we are much better. That's general. That's every benchmark that you're likely to see. Often the devil is in the detail, and too often, unfortunately, the details are very rarely disclosed. It's benchmarking versus benchmarking. In this instance, what we'd like to do is stay as far away from possible and as be transparent as possible. So when we looked at some of the blog posts that were already published, the first one, the blog that Ivan wrote, that was operating on 3 billion documents. The next person to come along and say they could better that, also doing 1 million writes, but only on a data set of 1 million documents. So already they were kind of tweaking the parameters in their own favor. So what we did in our experiment was we matched Ivan identically, and like I say, we want to be as transparent as possible. So all of the information about this is publicly available. We've got the facts and figures up here, and even at the bottom there's a link to the GitHub repo, and we encourage you to actually give this a try for yourself. If there are free credits available, why not spend those free credits, seeing how fast you can make Couchbase perform. So so we were interested in doing a pure write workload on a data set size of 3 billion documents, making sure we touched all of those 3 billion documents, so touching 100% of it. The documents were 200 bytes large. Durable writes, so making sure that this wasn't a fire and forget scenario, that these were writes that the client application was aware had been persisted, and I'll talk a little bit more about what that means on the next slide. We're measuring two things. One is the high level number of operations per second, the number of nodes we took to achieve that, and the answer is there in the bottom corner. We were able to replicate exactly the same benchmark that Ivan had with his 300 nodes on 50 of nodes of exactly the same type. So these are the N1 standard 16s. They're a very nice sweet spot for Couchbase. For anyone that's not familiar with the Google Compute nodes, these are 16 CPU cores, about 60 gigs of RAM, and we complemented that with a 500 gig SSD. So let me mention a quick bit more about the durability. What do we mean? So 1 million writes. There are slightly different flavors of writes. So let me talk about what the writes were and how we measure them. So here's how the Couchbase writes work. So at the top you have your client application. That will write to our in-memory cache, and as soon as that write has been received, the write will be acknowledged and notifications sent back to the server that write has been completed successfully. At that point, two things are also going to happen asynchronously. So that write is going to be pushed onto a queue to be put on the disk for persistence, and it's also going onto a replication queue. So that write is going to be replicated to another node in the cluster. So your writes are technically available in two places. One is on disk, another is on a different node in the cluster. Now, for this benchmark, when we say a persistent write, what we mean is that node has been it's not just been acknowledged into the RAM cache, but the client has received notification from a second server that it also has a copy of the write. And we would say this is the correct way to measure a durable or a persistent write, because not only do you allow for the fact that node becomes unavailable, but also that node's storage becomes unavailable as well. Moving a write to an entirely separate server is a more secure way than just relying on the disk. So when we're talking about the latency here that we achieved with our 1 million writes, we started the stopwatch when the client application fired off the write, and we only stop the stopwatch on our latency calculation when the write is acknowledged on a second server. So that's how we achieved our persistent writes. Okay, that all makes sense? You nods? Yep, thumbs up, grand.
Did we lose the connection?
I don't know, I can't work your...
It's a live thing.
Perfect. So just to clarify the environment, like I say, we had 50 servers of the N1 16 standard. You can see the spec there. This was using Couchbase 302, using one of the standard Debian OS image. And to drive this, we used 32 clients. The clients didn't need to be particularly memory intensive, so we used the high CPU 8 variants with 8 CPUs. And this was running one of our, in order to generate the documents and record the latencies, this was using our standard load generator Pillow Fight, which comes with libcouchbase. So in order to get the top-end performance, in order to be able to get the best latency and the lowest number of servers, a little bit of tuning was required. But one of the things that really, really impressed us with the Google platform was how much performance we got straight out of the box. Create an instance, install Couchbase, run the load generator, and I say we were able to achieve roughly 90% of the performance without any tuning whatsoever. Did a couple of tweaks on the OS, so it was an ext4 file system. We disabled journalism. Didn't disable journalism, but disabled journaling to get the very best performance. And put the Couchbase data volume on a separate partition to the root volume. So the only transactions going to the data volume were Couchbase operations themselves. It took the most of the tuning actually went on the client side. So if anyone's had any experience of Pillow Fight before our load generator, it's an absolute fire hose. It's an absolute beast at generating traffic. And actually, if you're not careful with it, it can get to the point where it overwhelms the cluster. So what we needed to do, we actually needed to make a couple of modifications to Pillow Fight itself, not to operate in a completely unconstrained fashion, but actually to deliver a buffer of operations rather than just fire operations as fast as they possibly could. So a few tweaks which have now been published again on the Pillow Fight up on GitHub. Those changes have all been pushed back to the mainstream. So on the Couchbase server, again, very, very few optimizations or tuning required. We changed because this is a write-intensive workload, the default compaction threshold, that's the threshold where your on-disk files will be compressed and all the redundant operations extracted. Because this is a write-intensive workload, with our default compaction threshold, compaction kicks in pretty much straight away. In order to get the best performance, we just moved the compaction threshold to a higher number. And we actually tuned down the number of writer threads. Because the Google storage performance was so fast, we didn't actually need all of the writer threads pushing those operations to disk. The disks were sufficiently fast so that 2 writer threads were able to operate quick enough. And actually, those instead of using those threads to perform the writes, those threads were better spent accepting the front-end operations. So instead of having more threads write into disk faster, we actually got better performance by having an additional number of threads service the front-end operations. So with that tuning, here's the full result. So I'd say for the 3 billion data set we thought was the more relevant. I thought it was slightly cheeky of the competitors to operate on a subset of that. But with that configuration, we median latency of just 14 milliseconds. Again, 3 billion documents and 1.1 million writes per second, 1 million persistent writes per second. And when you add up the total bill, at the time we ran the benchmark, it was $56 an hour. Ivan mentioned that Google have recently applied some discounts, so now that's $45.90 an hour. And we think that's pretty impressive price performance from Couchbase.
I want to give another plug to my guys. Actually, what happens is this is list price. So instead of asking you to sign for a long-term contract, what we do is we do sustain use discount. So if you take this workload and use it for a month, you're gonna get all the way up to 30% discount on top of this price. So what we do is as you launch VMs and tear them down, we average the number of VMs that you use for the period of time, and we're going to give you a proportional discount for that. So usually, the type of prices you see are lower than list price without you having to sink money up front.
Thanks. And then for the second workload, so if you have a slightly smaller data set, 100 million documents rather than 3 billion documents, we can still do those. You need fewer nodes, you need slightly smaller nodes. So instead of the 50 N1 standard 16s, We use the 40 of the standard 8s, and then so you can do, if it's just the number of operations you're interested in, you can do those 1 million writes per second, again the persistent writes, for just $17 an hour, which is pretty stunning. So overall, we were tremendously impressed with how well Couchbase performed and how flexible Google's platform was. The two are a very good match for each other. If you, with the scripts that we've got up on GitHub, we're able to deploy a cluster of 50 nodes, handling all of this data in around about 20 minutes from start to finish. So the provisioning time is fantastic. The command line, the management interface is pretty nice. The console that they give you, but the command line tools are even better. Quite a rich and very straightforward script and API to be able to create these instances on Google. And again, the results speak for themselves. Very, very low latency, very high throughput, and at a very reasonable price. Okay, that's us. So where is that time being spent in the 20 minutes? Okay. Yeah, sure. So the actual time to create an instance is probably less than a minute. So the reason it took 20 minutes is just a case of how parallel you go. So we were probably doing 5 at a time. So the way the scripts are structured is that we first of all create a single instance. We create an instance. We install Couchbase, and then we create a snapshot. And then for the rest of the nodes in the cluster, we use that snapshot to create them. So you're probably talking about 10 minutes to create the initial snapshot, and then 10 minutes to provision the rest of the 50 nodes based on that snapshot itself. Yes, roughly to pull down the Couchbase off the internet and install it and disable the journaling, etc. Okay, another question?
Just a quick thing on the VM creation. We don't have this as an SLA, but we have an internal metric that we want to be able to launch 1,000 VMs in 5 minutes or less. So we think that's an absurd enough number that everybody should probably be comfortable with it.
I have a quick question, specific question regarding Google Computer Engine. How do you guys handle situations like timeout, concur, rate limit, like number of concurrent requests, some kind of issues?
So on Compute Engine, how we deal with number of concurrent issues, concurrent requests.
You know, for example, I spin off 300 nodes, and in certain region or Windows zone, it might be no response or whatever. So how do you handle those kind of situations? In any distribution system, there are lots of issues. Rate limited, number of concurrent requests is limited, right?
Yeah. So most of our APIs, they have rate limits to reduce abuse. So if you go through the command line will handle that for you. If you go through API and you make the calls directly, then you're gonna have to handle basically the rate limits. Pretty much every rate limit we have is policy, not limitation. So if you have the need for something higher, you can talk to any of us, and we'll bump for a project.
You don't have any sort of you have a COI definitely, right? You don't have any API, and even
No, we do actually. Yeah, it's called API. Most of our services have REST versions.
don't allow user to specify some kind of parameters in terms of similar to SLA, number of concurrent requests, timeout, threshold, how big it is. You don't have those kind of things that allow user to specify.
It depends on the product. Right now, even on Google Compute Engine, right? So for instance, you will have an SLA for disk performance. If you use the UI, it's right on the UI. If you use the command line, you're going to have to read the manual, right? Because the command line is very short in terms of what it plots. But in terms of API calls, then no, you get a daily quota, and then if you need a bigger quota, there's support packages that you can buy, and they'll bump your limits.
Yeah, that limits the number of nodes or those kind of things. But anyway.
I think there was one said there was another one just here in front of the column first.
So, could you run your experiment against multiple cloud providers to kind of see what you would get against competitors if you were thinking about picking one solution over another?
Yes, for sure, yes. But it's not really the business we want to be in. I mean, our customers will need to make up their own choices, and we basically need to be Switzerland. At the same time, we'd love Ivan to stand there and say, Couchbase go way faster than everyone else. Of course, the nature of our two businesses are that we can't like express a preference or we publish our results, even though internally we might do our own benchmarking.
I am excited about your question. Thank you very much for asking it. As part of my job, so the question is, can we run those benchmarks on other providers and do an apples to apples comparison and say if we're better or not? So the short answer for that is actually no, because at least I cannot. The EULA for the other providers, if you read it carefully, you go blind. So read the EULA and you're going to see that I cannot actually publish comparison benchmarks. So we did one better. My team went out and reached out to pretty much everyone you can name, and we got 30 companies to sign up with us to launch what we call Perfect Benchmarker. The link is at the bottom of the slide. And what we have is we have 26 different workloads, including NoSQL workloads. They're all open source. It's on GitHub. You can contribute. You can open issues. And it's a single --Azure --AWS --Google. And they will run the stuff on your account on each one of those providers. And you're going to be able to compare the results. As a gift, we added a whole dashboarding solution for you so you can have pretty charts to see the results. Check it out. That's actually my day job, so it's fun.
But there's a gentleman who's been very patient. I'll be honest, I chose Debian because it was the first one on the list.
Very scientific.
Yeah. A question right at the back? Yeah. So that was, so again, it wasn't when we found that we were running the benchmark, it's actually it was actually quite CPU intensive in order to take the writes and things like that, and which is why we mentioned we actually tuned the number of writer threads down, because you're absolutely right that the disks were capable of sustaining quite a few more. Yeah, absolutely. There's another question here at the side. Not switched off. We increased the threshold. Yes.
So essentially, so I'm wondering what happens if you have compaction running and spend long, because that's the real life scenario.
Yes and no. So the question was, hey, how did you perform with you moved compaction out of the way? We didn't move it entirely out of the way. We just increased the threshold because if we didn't, on a pure write workload, compaction would basically be running perpetually. which isn't a real life scenario. We would always encourage customers to run it in 4, and again, a purely write workload is actually quite rare. Most of our customers are running workloads that are dominated by reads. But to answer your specific question, hey, what happens when compaction kicks in? As consistent with the gentleman that asked at the back there, the disks are capable of sustaining far more operations, so it's no problem at all for the storage to accommodate the additional disk workload run by compaction. You might need an extra few nodes to account for the additional CPU requirement that compaction will induce as it's going through the couch store file, pruning the B tree, etc.
Yeah, I have a question
Sure.
on Google Companion. How does GC handle jet and Skew for a very large cluster? Suppose I spin off a cluster with 50K nodes in parallel. In that case, on that cluster, there are so many nodes, right? I mean, typically we use MTPD. I mean, the time difference on each node will be significant. So how does the GC handle that?
So the question is, if I have a cluster large enough, what happens to my clock skew? Oh, you're gonna have clock skew. You know, it synchronizes with the host, but you will have clock skew. So synchronization and resolution through timestamp is not exactly transactional. You're gonna have problems with that.
What is
So
your theoretical threshold? Like beyond 50K nodes, we cannot do it in parallel. It will be not that good. Of course,
I don't know that number top of my head. I could measure it. 15,000 nodes, though, you probably 50,000 nodes. You're probably gonna have to ask for a special quota for that. Right. Yeah, we did clusters that big, and if you buy something like that, I'm pretty sure we'll find a way to to accommodate. So I can tell you, Spanner. Spanner uses an atomic clock, and that basically has no clock skew.
Oh, your global database, right?
Yes, we use atomic clocks on each data center. So every few millennia, we're gonna have half second of error. But if you really want that level of transactionality, right, you need to implement two-phase commit.
Performance-wise, GC is much better than AWS because GC has no technical debt, which is no legacy.
I love your optimism. I'm gonna stop talking now.
There's another question here. I think we've got about 5 minutes, just under 5 minutes left. So we'll try and. Yes. Yeah, so the question there was, we picked a document size of 200 bytes. Why did we pick that document size? And then what happens if the document size increases? So the first reason, again, very very simple, like Debian, we picked 200 bytes because that was the statement that had already been made. That was Ivan's choice.
That was my fault. That's it. When we opened the performance team, right, I needed to figure out whether what we had was interesting enough. So I went out and I dig up a Netflix benchmark from 5 years ago, and they use this stuff for telemetry. And I say, you know what, let me just measure this one real-life scenario to see how we do. And then the blog post I published was basically like, hey, we can do this for half price. That was it. And then they saw that blog post and say, yeah, half price is expensive. I can do this with way less. Right? So the size it came from. I almost feel like telling the story of why roads are as wide as they are, and you go back and you see is the size of the back of a Roman horse. Right? So yes, the size come back of this completely arbitrary benchmark Netflix run a eon ago. Right? Sorry.
So then the second half of the question is, hey, well, what happens if you increase them? And then so we did some experiments, and there's basically, although I've not got any numbers or science to show you, but again, anecdotally, you increase the size of the documents, and you can maybe double or triple the size of them, maybe up to around about 1K, with no really appreciable difference in the performance. You might not quite hit the 1.1 million, but you're not too far off it. You may be slightly under. And then, but as you increase, there are going to be other things like the network traffic's obviously going to increase, and then it becomes a performance of it. How close do you get to your disk threshold and things? So it really, I mean, I would invite you to run it for yourself and play. There's so many with these games. It was a fascinating task to take on, because there are so many things you can try. Play with different node sizes, different storage types, different document sizes, different persistence requirements, different workload mixes, and things like that. So yeah, for sure you will get slightly different, but I think in the short term, like a double or a tripling of the document size wouldn't make too much difference to the top end performance there. Any other questions? Go on. Yeah, that's an excellent point. So the statement here was, when you do increase your document sizes, you can get to the situation where your data set is greater than the memory quota on your node, and so some of your CPU cycles are going to be dedicated to managing that cache. Like Couchbase, when we have we hit the high water mark, and then we eject some items to disk, and so yes, there will be a penalty. But then again, that's the actual what. In terms of quantifying that impact, that's going to be on exactly how big your documents are, how big your quota is on each of the nodes, and it's another one of the other many experiments that could be performed. Final question?
Anecdotal numbers for instead of considering a write after it replicates, but after a persistent disk?
Sorry, say that again.
Have you tried considering a write after persistent disk rather than replicate? Play around that?
No, because we decided quite early on that what we would say that the correct way of doing persistence would be the time that it's available on another node. So safe from the node failing, from the disk being lost. So no, again, another way you could slice this. I'll give you a slightly different frame of reference though. One thing we did. And we did this as a demonstration at one of the conferences in Europe, is what if we take a much heavier read workload? So if we did 95% reads and only 5% writes, and we had, numbers off the top of my head, I think we had 6 nodes doing about 8 million operations a second, slightly different document sizes, but kind of, it just goes to show all of this, the benchmarks are very, very dependent on exactly the specifics, which is why we've tried to be as transparent as possible. But again, and as another data point, the N1 standard 16 instances, 6 of those nodes doing a 95% read workload, we were able to push about 8 million operations a second through the cluster. Okay?
Just a final thing. To say, like, to run this benchmark, you're probably going to have to bump your CPU quota up, because this cluster is a little too big, so try to run a smaller one, proportionally smaller. The other things, like, we check it out, check our products. We really appreciate your business. We're trying to innovate on our products as much as possible. We just launched something called preemptible VMs, which is, if you have a batch job and you don't care, you can buy this VM that costs a fraction of the price, right? But you might be preempted. No more than once a day. That's the thing that we have. And we do several studies on I/O patterns, for instance, right? So when you issue the I/Os, we don't get to see what you're doing, but we get to see what the guest OS is issuing. So we detect forward patterns, backward patterns, strides, and whatnot, and we keep optimizing for that. So our products get faster as we tune in and we put more intelligence into how those virtual devices actually work. Thank you.
Okay, that's us. Thank you very much.